Hello. Today we're going to start to explore the idea of what a sampling distribution is. Now, this is a pretty important idea. It is going to, for one, it's going to bridge the chapters that we learned previously, chapters 1 through 6, the ideas of organizing data and collecting data and probability. It's going to connect all of those chapters to the idea of statistical inference, which is the process of taking data and trying to make an educated guess using the data. So this chapter, understanding sampling distributions and how sampling distributions, the traits and characteristics of them, will allow us to fully understand statistical inference. So it's a fairly important idea. So the first section, so today's lesson is going to be about what is a sampling distribution? How do you define a sampling distribution? To start off with, let's revisit this slide. We've seen this previously in the course. The idea of statistical inference is that you have some large population in which you'd like to find out information upon. Now, ideally, in a population, what you do is you just collect information on every individual in the population. This would give you the best data. However, that's really, really time consuming. That's the idea of taking a census, and to take a census is really expensive usually and time consuming. So instead of taking a census, we take a sample, and we use that sample to come up with an idea or some sort of conjecture as to what we think is true about the large population. Now, when you take a sample, you get information about that sample. You can find the mean of the sample or the proportion in the sample that say yes, or the standard deviation in the sample. All of those are called statistics. Statistics are numbers that describe the sample. And oftentimes we're looking at statistics. And those numbers describe that small set of individuals well. But what we're going to do is we're going to use those statistics to try and estimate parameters. A parameter is a number that describes a population. So if I want to know the proportion of people in the country that will vote for candidate X, knowing that information would be called knowing the parameter. Or if I want to know the average ACT score of all the students in the school, if I had that information, I'd actually have the parameter. So what happens sometimes is we actually have parameters. If, for instance, your teacher tells you the average score on a test after a test gets done, what they're actually giving you is not a statistic, but they're giving you a parameter. So we don't use that term very often, but we do sometimes use that idea. However, when the population is large enough, we usually don't collect the parameter because, again, it's too time consuming. So what we'll do is we'll take a sample, we'll get a statistic, and we use that statistic as an estimate of the parameter. Now, the thing about statistics, though, and when we use statistics to estimate parameters, is that the statistics that we get might not be exactly correct. They might be a little low or it might be a little high. If I want to figure out the average ACT score of all the students in the school, if instead of taking and finding everyone's ACT score and averaging them out, I decided to take a sample of 20 students from the school, the 20 students I sample might be different than the 20 students you sample, or the 20 students the student next to you samples. All those samples will involve different individuals. And because those samples involve different individuals, the statistic we get will be different. My statistic, which is my sample mean, the average ACT score of my 20 students will be different than the average ACT score of your 20 students. And because all those averages are slightly different, that's the idea of sampling variability. Because the sample that I get, the 20 students I have and the 20 students you have are different, we have something called sampling variability. Now, because of this, our statistics will be different. The statistic that I get and the statistic that you get will vary. They won't always be exactly the same, and oftentimes it won't be the same. And understanding how much they vary is an important idea. It's a crucially important idea. Okay. Now, collecting these sample statistics. So in the example of the average ACT score, the sample mean I get of my 20 students and the sample mean you get and the sample mean someone else gets. If we put all these samples together, and we did it over and over again, and we did it in a way that collected all the possible different groups of 20 we could have, we'd get something called the sampling distribution. Now, this is the idea. This is the important idea of this section of this lesson, is to understand what a sampling distribution is. Now, again, the idea is that if there are 400 students in our school, and I take a sample of 20, and you take a sample of 20, and a bunch of people take a sample of 20, that's not enough. That's just the start of the sampling distribution if we started to plot all these sample means. To actually get the full sampling distribution, we have to take every possible combination of 20 students that you could out of 400. Now we can look at what that looks like, and this is why it can be so hard for students. It's because it's actually such a large number. So if we look at this, we're looking at 400 things, and we're taking them in combinations of 20 at a time. So this is a probability idea with combinations. So we have 400 students, and we're taking them in combinations of 20 at a time. This is the total number of different groups we could have. Now that's a staggeringly large number. So to get the true sampling distribution, we'd have to have this many different samples. And with each of these samples, we'd calculate the mean, and then we'd plot all of those means on a graph, and then look at that graph. And since there's so many, we'd probably plot it and make a density curve out of it, and look at what that density curve looked like. Now, that's why the idea of a sampling distribution can be so hard, because you have to understand that it's all possible samples of a certain sample size. Now, because this number is so big, we actually don't usually ever find the complete sampling distribution because there's just so many different options. But we use mathematical theory and calculations to know what this sampling distribution will look like, what the characteristics are of this sampling distribution. Okay. So that's why it says in here, it says in practice, it's difficult to take all possible samples of size n. Okay. So we use simulation to imitate it, or to kind of start to create it. And you can use computer simulation to start to make that, because a computer actually could run through that many different possible options. So there are three types of distributions that we want to explore, and we want to make sure we understand the differences and the distinctions between them. There's the distribution of the population, which is called the population distribution. There's the distribution of the sample data that we've collected, okay? And then there's the sampling distribution. And all three of those things are different. And this slide will kind of give you a picture of what they look like in a problem involving proportions. So in this particular example, we have a population that involves 200 red and blue chips, okay? So like poker chips. And 100 of them are blue and 100 of them are red. So the population distribution is this graph right here. Okay? It's a bar graph. It has blue and red as the categories, because it's categorical information. And there's 100 blue and 100 red, so the bars go up to 100 for each of those. So that's the population distribution. It shows all the information about the population regarding the proportion of blue and red. Now, the distribution of sample data, if I took a sample of 20 of these chips, right, if I had them in a big bag and I shook them up and I grabbed out 20, this is one possible option I might get. I might get 12 blue and I might get 8 red. And therefore, the sample proportion I get, as far as the sample proportion of red, is 40%. I got 40% red. And that sample proportion is labeled with p hat. Now the population proportion is labeled with p, and the sample proportion is labeled with p hat. When we talk about parameters, we use p, and we use mu, and we use sigma. When we talk about statistics, we use p hat and x bar and s of x. So we have different notation for these statistics and parameters. So p hat is a representation of the sample proportion. And in this case, 40% of the sample I took were red. Now, I might throw them back in and take another sample. That next sample I get, the distribution of the sample could look like this, 9 and 11, which means my sample statistic was 55%. Okay. Now, so the actual distribution of the sample are these bar graphs. The sample statistics are these things to the right. And this is then the third sample I took. I put them back in, I shook them up, I took out 20 again. This time I got 13 red ones and 7 blue ones. In this case, 65% red. That's my sample statistic. In this case, I'm looking at the sample proportion. Now, if I kept doing this over and over again, I kept throwing the chips back in and taking them out, putting them back in and taking them out, and I kept track of all of these proportions, all of these p hat values, I'd start to get a sampling distribution. And this is what a sampling distribution would look like. It's a distribution, so a graph or data showing where the information falls or lies. That's what a distribution is of a statistic. Okay, so a sampling distribution, what it is it's a distribution of a specific statistic. So you can have a sampling distribution of p hat. You can have a sampling distribution of x bar, a sampling distribution of s of x, a sampling distribution of the IQR. Okay, what it means is that you've taken samples repeatedly and calculated a specific statistic, and then you plot or display what values that statistic takes on. Okay, so what we're displaying here is we're displaying all of the possible p hat values that we got when we took a sample of size 20 out of this bag and calculated the proportion. So these are all the possible proportions that we got. And what you're seeing, and this is important, is that the center of this distribution is 50%. And hopefully that's what you'd expect, because in reality, 50% of the chips were red. So if you sample over and over again, you expect to get 50%. Now, sometimes you don't. As you saw, sometimes we got 40 and 55 and 65. But sometimes you're going to get 50%. And actually, 50% is the most likely outcome. That's the expected outcome when you take a sample. So that's the one that occurs the most often. And as you move away from 50%, right, as you move to the right and the left over and over again, each of those outcomes are going to become less and less likely because it would be less usual, right? If you had 50% of the chips to be red, it'd be pretty unusual to pull out a sample of 20 and get 80% of them to be red, to get 16 red ones and only 4 blue ones. That would be unusual. Now, as you can see in this sampling distribution, it does happen, but it doesn't happen very often. I'd say this is actually not a full sampling distribution. This is just the start of one. Because if this was a full sampling distribution, it would be symmetric. The probability of getting 55% red and 45% red would have been equal. So this is the start of the sampling distribution of the proportion of red and blue chips that we get. All right, so that was the big idea, what a sampling distribution is, and we're going to learn a little bit more about that. So the center of the sampling distribution should be equal to the parameter that we're trying to estimate, and that is going to be true if we're doing it in a way that's unbiased. So if we collect the data randomly, so if we do simple random samples or some sample that's random, then it should be unbiased. And then the center of the sampling distribution should be equal to the parameter that we're trying to estimate. Like it was in this case, right? The center of this was 50%. The true parameter was indeed 50%. And that's if we took simple random samples, which it says we're doing here, simple random samples of 20. Okay, so that's why taking a simple random sample is going to become so important. It will help us to collect data which will reasonably estimate the parameter. Okay. The second part is sample size. Okay. So the more data we collect, the more accurate we expect the information to be. And this is actually fairly easy to talk about. If we, let's say you flip a coin. If you flip a coin 4 times, it's probably pretty likely that you could get 3 heads or you could get 3 tails. Okay? Those are actually the 2 most likely outcomes other than 2 heads, which means you'd have 75% heads or 25% heads. Okay? So the proportion of heads is going to vary fairly large. You might get 0, you might get no heads. That's not going to be real common, but it's going to happen 1 in 16 times. Now, if you flip a coin 40 times, okay, so if you increase the amount of data you collect, the probability of you getting 30 heads or 10 heads is really, really small. Okay? And the probability you get 40 or 0 is virtually 0. Okay? So the more data you collect, and I think this is intuitive, the more data you collect, the more accurate your data becomes, the closer it gets to the truth. Okay? And that's what we're seeing in this picture. If you take a samples of size 100 and look at the sampling distribution, there's going to be quite a bit of variability from 22 to 52%. But if you take samples of size 1,000, the variability here drops from 31 to 43%. Okay? In this startup sampling distribution. Okay? So the variability will be completely dependent on your sample size. The larger the sample, the smaller the spread. So looking at those two ideas together, bias and variability, what we'd like to have is particularly we want to have low bias. Okay? And if you look at these 2 bullseyes, the 2 pictures on the right, both are low in bias. The 2 pictures on the left are high in bias, meaning the ones on the left are systematically favoring a certain outcome. They're systematically favoring you throwing the dart kind of high and to the right. Okay? Now, of these pictures then as well, the one on the top left and the one on the bottom right have low variability, which means you're consistently hitting your mark. Okay? Now, what we're shooting for, of course, is the bottom right. We can't always get that. But as long as you do a simple random sample, we should get one of the ones on the right. And the more data we collect, the closer we'll get to the one on the bottom right, okay? Because we'll get lower variability. Okay. Now, sampling distributions take on lots of different shapes. It depends on what you're using as your statistic. We're oftentimes going to be using means and proportions, but you can use other things, and that's a valuable thing for you to understand. Sometimes you'll see sampling distributions that will involve plotting sample IQRs or sample ranges or sample maxes or mins. So that's something that will be important to just kind of keep in the back of your brain, although it's not going to come up all that often. Now, that kind of wraps up the idea of sampling distributions. Make sure if you have questions on what a sampling distribution is, you continue to study it. You ask questions, you maybe watch this again, you look at other things, because it is a very important idea for us to understand statistical inference. All right, well, we'll see you next time.